Okay, this booklet has clicker quiz questions embedded in it. My goal today is to get through that whole thing. It's an ambitious goal. You need one.
I only wanted one to
Yes. Okay? It's an ambitious goal. Okay, so let's begin. A little bit of the start is introductory, review. That's not a problem. Any study in physics is best approached by beginning with the simplest form of a concept, followed by adding complexities as each step is understood. That's what we do when we design curriculum in any course, whether it's science or English or whatever, right? You start with basics and you expand. The concept of motion and its analysis is fundamental physics. Consequently, we will begin our study with this concept. Philosophers and scientists at the beginning of time have observed and speculated on the nature of motion, but interestingly, the concepts they developed for approximately 2,000 years until Galileo's time were unfortunately completely incorrect. And every time I think of this, or every time I read that statement, I cannot help but think, how far would mankind be advanced? Aristotle was the guy about 500 BC who came up with these ideas about motion, and basically everybody just believed him for the next 2,000 years. And we advanced pretty much no advancement with all in science for those 2,000 years. And it wasn't until late 1500s when Galileo came around and said, you know what, I'm going to have a look at this Aristotle stuff and I'm going to see if he's right. And it turns out, he was wrong.
What did he say?
Well, for example, one of the things he said, and he didn't come right out and say it, Aristotle, but one of the things that is implied from his teaching was that if you have like a really large, say a 10 kilogram ball and a 1 kilogram ball, and you climb to the Leaning Tower of Pisa, that you all know that Galileo climbed, and drop those balls, Aristotle actually said, well, the 10-pound one would get there not just quicker, 10 times quicker. 100 times bigger, 100 times faster. So how hard, for 2,000 years, nobody thought, I'm going to give that a whirl. Now, my guess is that likely someone did give it a whirl, but they were probably shunned and ridiculed and maybe shot or flagged. I said would be shot back then, right? Burned at the stake, what have you, right? It was Galileo who actually managed to, make people believe him. Interestingly enough, he was put under house arrest, and there's a video later in the course. He was actually put under house arrest by the church, and that's what actually gave him time to do some of these experiments that sort of explored the mistakes that Aristotle had for all the years. But just think, here we are today in 2013, and we got clickers, and we got smartphones, and we got, missions to Mars and stuff like that. And that's all happened since, Galileo. And if we hadn't been so stalled on Aristotle for 2,000 years, man, would we have a cool society right now, wouldn't we? All that cool stuff. So, anyways, question. It is still pretty cool. Question and make sure. Okay, so our study of motion will begin by analyzing in its simplest form, analyzing the motion alone without being concerned about its cause. We're not going to worry about forces yet. Okay, we'll get to that next unit. By allowing the motion to occur in a straight line only. Does anybody remember what that's called? Straight line motion. Starts with a T. There's no rotating. Very close. Translational. Translational. I'm not sure what happened over there. But translational motion. Oh, yeah? Okay. This is called straight line kinematics. In order to study straight line kinematics most effectively, we will look at the simplest concepts first and use them to develop blah, 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 blah. We're going to use a train, blah, 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 blah. Okay. In order to illustrate the concepts of position and displacement, we're going to use a locomotive, a train moving back and forth in front of a station as it shunts rail cars. So it's moving these rail cars back and forth. Remember that the track is straight. The train station is a reference point for analyzing the motion of the locomotive. We're going to call it 0. We're going to call it the origin. As we stand at the station, we notice that the locomotive is 50 meters to our left. Sometime later, it's right in front of us. Still later, it's 40 meters to our right. And later, it's located 10 meters to our left again, moving all around. We could draw a diagram to represent the various locations of the locomotive as they're measured from our reference point, the station. So the X1 indicates the first position of the locomotive. And X1, do you guys have it on yours?
Yeah.
You do, but I don't. That kind of sucks. So X1 is where?
60.
50 to our left, so at minus 50. X1, is that where you guys have it?
Yes.
Okay, and X2, right in front of us. Is it a 0? X2 is there. X3, 40 meters to our right. and x4 10 minutes or so. X4 is right there. Notice that I'm using X for position. Remember, a position time graph, the position is on the y-axis. Don't get that confused. Okay. Note that the position is always measured from a reference point and always has a sign associated with it. You can probably get away with not including the plus sign. It might be a good idea today just to include it, just to sort of solidify it, positives to the right. If we were to analyze the motion of locomotive, we would need to know its change in position as it moves back and forth in front of the train station. Anytime there is change in position of an object, we say that it has undergone displacement. That's supposed to be an underline. My highlighter is gone. Okay, so displacement is change in position. Now, if we want to determine any change in position, we would subtract where we started from where we ended up. We learned this when we did vectors. I did 2 dimensions in vectors, right? Displacement, or delta x, is xf minus xi. Right? The symbol delta. Anybody know what the symbol delta, where it comes from?
Greek alphabet.
Greek alphabet. It's the letter D. D. Interestingly enough, being the nerd that I am, when I was in Greece, I guess 2 or 3 summers ago now, I could actually read words. I had no idea what they meant, but I could read them because I knew most of the Greek alphabet. So I could sort of, if it was kind of like a modern word, then I could sometimes figure it out. So that was kind of neat, I thought. Here's a good question for you. The physics students in Greece, what do they use for change in x? Do they use delta?
Like, they use hours.
I don't know. I'd like to know that, Joey. Like, some nights I wake up in the middle of the night, I wonder that.
They use hours.
I had some students that went to Greece on travel club. They said they were going to find out for me, but they felt a little self-conscious asking people that question. Oddly enough. They didn't want to stop people and say, "Hey, do you take physics in school? What do you use for delta?" Kind of weird.
Is it modern Grecian language different than like ancient?
No.
Greek?
No. They still speak Greek.
Yeah.
And they still use.
It would change.
They still use well, I mean, they talk about TV and telephone and stuff like that, right? But I mean, there's, Greek words that have been around forever. Yeah. They still use the same alphabet.
We still use the same alphabet.
That's true. Yeah. Okay, enough of my rantings. The symbol delta is a much used symbol in physics, which indicates a change in something and always subtracts the initial from the final. The displacement of the locomotive for the first interval can now be calculated. So you will remember we were at minus 50 and we ended up at 0, right? So my displacement is going to be 0 minus 50. My displacement is plus 50 or 50 to the right. Correct? Displacement? Okay, so now you're going to do the next few here. This tells us that the locomotive moved 50 meters in a positive direction, which is to the right. Calculate the displacements for the other 2 time intervals. Now, do you have this on yours? What do you guys have? Yeah, so interval 2 and interval 3. So go ahead and figure out the displacement for interval 2. Yeah, go ahead and use the clicker and figure out the displacement for interval 2. I think these are single questions, yes. So you can only do one at a time. So go ahead and do the first one. Tell me what's the displacement for interval 2 between x2 and x3. Okay, you're finding the displacement between position 2 and position 3. Position 2, I think it's at 0, is it not? Position 3, it's at 40. So hopefully, everybody got it right? Almost. Plus 40, right? Is it not plus 40? Right? So it's going to be x3 minus x2. Right? x3 is 40. Oh, sorry, that's 2. x2, 0. 40. Okay. Right? Good? Go ahead. x3 to x4. Okay, so waiting for Zach here. Interval 3, 3 is at what? X3 is at 40, x4 is at minus 10. So what's it going to be? It's going to be x4 minus x3 minus 10 subtract, what is it? 40. I hope you all got it.
Yeah, we need to see what percentage this one.
Oh, couple of boo-boos in there, eh? All right, well, hopefully we get that eventually here. Okay, so now you've got, I believe, there are several questions here now. There's 1A, B, C, D, E, 2A, B, C, D, and then there's, when you get to number 3, I have to change it on the board here, but you guys can just keep going, okay? So these are all clicker. I'm going to start this right now. Okay, so you're finding the displacement for each of the following changes in position. Minus 8 to 2. 2 to minus 8, and so on. There's... Okay, number 10 on your clicker is a multiple choice. You have to refer to the screen to do number 10. I'll give you a few minutes. All right, quickly, some answers here. Most people did pretty good. The first one here is, of course, plus 6. The next one here is minus 10. Is that right? You guys get the answers on your clicker or no? No? Well, they're all right. I guess, yeah. 0 to 8, of course, is plus 8. Minus 8 to 20. Plus 28. 8 to minus 8. You're kidding me. Minus 16. What'd you do, Ryan?
I put 5.5 instead of 5.50.
Yeah.
And it's wrong. I put 5.5.
Remind me to fix that one.
We're just simplifying it, right?
6 is minus 30. This one here? Oh, yeah. Well, you know why? Because now this is that whole sig fig thing. Yeah, I know. Go ahead. Go complain to someone. You should follow the same format that's given to you. It's okay, Ryan. I'm not going to record it. You go on a diet here. This is delta W minus 5. Randy has a question?
When you're answering these questions and you're lifting, is it delta W?
Yeah, in this case here, it says express delta W, so it would be equal to minus 5 kilograms. Correct, actually, right? Yeah. Oh, yeah. You mean W in the units?
Yeah, and like the delta.
No. Okay, number 9 goes from 20 meters above the ground into a hole 10 meters deep. Did you figure out what the 10 meters deep is? Minus 10. I didn't come right out and say what the origin is or the reference point, but what is it? The ground, absolutely, right? So delta x here, of course, is minus 30. Makes sense now, right? Okay, these ones here. So the displacements were the displacements here are plus 3, minus 9, plus 3, minus 3, plus 2, and I'm running in a room, minus 3, and plus 5. So which ones are the same? A and C and D and F. A and C and D and F. A and C. There is no D and F, so I guess it's B. Is that right? Correct answer B?
Yeah.
B. Everybody feels good about that? Sure. I hope so. You will not see questions quite that easy on a test. Yes. Oddly enough, every time I say that, I always get the same reaction. I don't know why. Position diagrams. Let's start talking about them a little bit more. Knowing the position of an object tells us about the motion of that object, but it would be helpful to know the length of time it takes to undergo the displacement. It's not good enough just to know displacement. We need to know time. Displacement and time can both be illustrated at the same time on a position-time graph. The position-time graph is capable of providing us with information about displacement, average velocity, and instantaneous velocity. Before I go any further, what do you think is the difference between average velocity and instantaneous velocity?
Changes at a certain instant.
1 instant time averages over, right? How many readings do you have to do to get instantaneous velocity? Like how many? Just one, but average?
More than 100. More than one.
More than one. 2 probably. Actually, average would be 2. Initial and final would be good. Oh, if as long as it's constant. Okay. These 3 calculations will be performed using the sample position time graph shown below. Okay, so displacement is determined on a position time graph using the standard formula. Displacement is delta x, xf minus xi. Remembering that the position here is not on the x-axis, it's where? When I say x, I mean position. I don't mean x-axis and y-axis. Okay? Don't confuse that. The final initial positions are located on the vertical coordinate. Fancy math teacher word for y-axis. The professors like to say vertical ordinate. I don't know what the difference between coordinate and ordinate is. I guess, yeah. If you desire, a dotted line can be drawn from the graph with the position coordinate in order to easily identify the 2 positions. In the example graph for time interval A, now see here's A. See that A at the top? So A is from 0 to, now you have to sort of use your imagination a little bit. I'm going right to there, because that's where the graph changes. Do you see that? Okay, so B is going to be like to there, C is like to there, D is like to there, E is like to there, and F is that. Does that make sense? Okay, so interval A is from 6 to 0. Where did I get the 6 from? Okay, so right here at, I guess that would be 2 seconds. Where is it? Plus 6. Okay, does everybody see the plus 6? Ryan's using his X-ray vision, but he sees the plus 6.
I see the plus 6.
Okay, what's the initial position? Right here at 0. Note I'm not talking about the x-axis. I'm talking about the position here. Okay, so that's your example. Guess what's coming? There, see that right there? 6, 0. Displacement is plus 6. Okay, let's go. I want you to determine the displacement for interval B, C, D, E, and F, and then answer this question right here at the end. Okay, let's see how we did. 100%, Steve?
Oh, I got one wrong.
Okay, correct answer for interval B is 0. Remember from yesterday, a flat line indicates stopped, no movement. Correct answer is 0. Interval C, what's your correct answer here?
Negative 16.
Negative 16? I sure wish this was very open.
I bombed it.
Minus 16, right?
How come there's so many different answers? I started at 8.
Interval D is 0. Yeah, you got to start at the right spot.
Exactly.
E, this little guy right here. 6. F, 4. And yes, as many people have pointed out, only Mr. Friesen can make this position time graph. Because of course he has a time machine. Did you know that he's currently 24 years old? Well, after you retired, you just jumped in and yeah. Although if that's the case, do you really think if he had a time machine that he would have stayed until? Why not just jump in it and not show up to school someday? Right? I guess you still need money, though, don't you?
No,
Okay.
You can steal money and then go forward in time so people can't catch you.
I suppose.
Yeah.
I don't know. I would like to point out.
People could catch you because you'd be in the same position and they just wait for you.
Exactly. Yeah, but
I would like to point out
eventually there's someone
that indeed you are sort of going back in time here, Jake and Hannah and a few others need to pay attention here. Okay, I need eyes up here. Okay, so yes, in fact, this particular thing is not only going back in time, but you could also say that it's actually in two places at the same time. Like at 2.5 hours, it's at 50 and it's 22 or something. That's impossible.
Or what about at 2 hours at the same time?
He's already left.
Like his house.
How many people remember the vertical line test from math? Yay! What does the vertical line test say, Dan? You remember? And what is that? It means that it's Riley's waving madly. He wants me to.
If it touches two lines,
Yeah.
If you draw a line like vertically down,
Yeah.
and if it touches 2 points,
Yes.
then like it's not right.
Not a function. That's the word I'm looking for. Okay. So I'm going to draw a vertical line like so, and I'm going to drag it from over here, right? Function, 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 function. Not a function.
Warning.
I think you get the idea. So you will see in books, you will say things that will say that the position is a function of time, which means that it can't be in two places at the same time. That's what it means. Okay? So on occasion you will see that. Okay. I want you to now. Oh, this is a. Okay. No, I think we're done with clickers. So you've got a few minutes left here. I would like you to complete these last two. And I'm going to give you another handout as well. That's going to go a long way to help me get the Tuesday go smooth. Go ahead and do these two. Okay, if I were to find the average velocity, say for the example one here, right? This is the example one. Remember this? Can you find this page in your book? The displacement was 6. How much time does that take? 2 seconds. So my average velocity, V bar, is my d over my t. What's my displacement? 6. How much time? 2 seconds. 3 meters per second. When you do the next one here, you guys got 0. How long did 0 take? 1, 2, 3, 4 seconds. So V bar is going to be 0 over 4, 0 meters per second. Stop. Right?
Okay.
Yeah.
Minus 16, D over T, minus 16 over how much time? 1, 2, 3, 4 seconds. Minus 4 meters per second. Can you go minus 4 meters per second?
Do you have all of those ones?
Absolutely. It just means you're going 4 meters per second to the left.
How do you put that?
You go minus 4 meters per second. That just means that. Okay? So what I want you to do is, and then I'll stop yakking at you. I want you to, I want you to go back to, I got to go back to the Word document. I want you to go back to here, right? And find the average velocity for each one of those intervals as well. Do that for the first position time graph as well as the last one. Okay? So find the average velocity for every interval. Find the average. I want you to do each one. I just haven't done it on here. Right? Do each one. I will tell you tomorrow. Try it. Watch the video.
Oh. I don't know, it's a bunch of numbers.
It won't take you long.
You just do the final part of it?
It'll take you less time than it will me to make the change in my question sheet.
So this is the handing sheet?
No, this isn't the handy. This is just practice. I'll give you answers tomorrow.
You don't have to decimal. So the last one was the last one.
Yeah. I just want one of the 7
.14 meters per second. Or, oh yeah.
Oh, yeah, I get it.
No, but if you reduce it, that's you're reducing the second. You have to go 1 over this. That says you're only moving 1.